Good afternoon, good morning, good evening, depending on where in the world you're joining us from today. Thank you so much for attending this Lunch and Learn webinar titled Activating Biochar from Dairy Manure, Research and On-Farm Potential. We're really excited to host this event on behalf of the SoilRes3 Lab in the Land and Food Systems faculty here at the University of British Columbia. And so today, I just want to start us off by humbly and respectfully acknowledging that the projects that we showcase are conducted on the traditional, ancestral, and unceded territories of the First Nations around British Columbia. We acknowledge the rights, interests, priorities, and concerns of all Indigenous peoples, First Nations, Métis, and Inuit, and we are committed to actively working towards reconciliation through our words and our actions. So you can feel free to drop the territory that you might be joining from. And as we continue through this conversation, just keeping in mind that Indigenous people have been active stewards of these lands for a time immemorial, and the work that we do in climate action is intended to support that work in becoming better stewards of our lands. So today, just a brief agenda of what we'll go over for today. We're currently at the top of the call, doing a bit of intro, and we'll frame today. We'll then move into some biochar basics and on-farm use. We'll then transition into dairy research around charged biochar, following that up with some cost-benefit lessons from biochar in the wine industry. We'll have a lot of time for discussion and Q&A after our presentations. And then we'll wrap up the lunch and learn session today with some next steps and some ways to stay informed. So with that, I'm going to give the floor to Associate Professor J.T. Cornelius. JT is associate professor in the applied biology in applied biology in the Faculty of Land and Food Systems at the University of British Columbia. He leads the SoilRes3 Lab, where his research program is directed at studying feedbacks between soil processes and biogeochemical cycling of elements in terrestrial environments. He's going to give us a brief introduction to this research project. So please feel free to take it away, JT.
Thanks so much, Novi. So, hi everyone, and as you know, folks, the health of soil, land, and people are strongly intertwined. And so the SoilRes3 Lab at UBC conducts interdisciplinary research on soil formation to understand how microscale processes drive macroscale ecosystem properties and resiliency. So through respect and reciprocity in relationship, the team works towards multidisciplinary and multicultural soil science approaches to support the effort of the land to maintain homeostasis. So in our lab, biochar serves as a very central hub to explore the intersection between soil-plant feedback, land-people relationship, and nutrient energy cycling in agroecosystems, with the ultimate goal of building living soils. So I'm very, very happy to see this webinar become a reality, bringing together dairy industry, consulting, and research partners to exchange on the use of biochar for nutrient management, material cycling, and on-farm decision making. So enjoy the webinar, folks. Thanks.
Wonderful. Thank you so much, JT. Okay, so we're going to transition into our first speaker. Corinna Howell is the current lab manager for the SoilRes3 Lab under Dr. J.T. Cornelius. She's working on building awareness and experimenting with biochar on farms in British Columbia to build resilient soils, food systems, and communities. Corinna recently graduated with a master's in soil science from the SoilRes3 Lab, and she's going to give us an intro to the basics of biochar. Thank you, Corinna.
Thanks so much. Good afternoon, everybody. Thank you so much for joining. So I am going to start by giving some context for manure production in British Columbia. I'll get into what biochar is, how it's produced, and then briefly how it can help farms tackle manure management challenges. So, the Fraser Valley in British Columbia is one of Canada's most intensively farmed areas, particularly recognized for its abundance of dairy and poultry farms. These farming operations contribute significantly to BC's organic waste stream, with livestock farms generating approximately 2.7 million tons of manure annually, and 65% of that is from dairy, 17% from poultry, and 14% from swine. So, manure is a critical resource to agriculture systems in the Fraser Valley, with most of it being applied to farmland locally, often on the same farm where it is produced, providing nutrients for crops and supporting soil fertility. However, in intensively farmed regions like the Fraser Valley, high manure production, when combined with limited land, poses significant manure management challenges for producers. First, productions are required to maintain 6 to 7 months of storage capacity for manure, as field application is restricted throughout the winter. This puts a heavy storage burden on livestock productions, and additionally, storage conditions and infrastructure bring additional regulations which further burden productions. Second, decades of dairy and poultry farms applying manure to the land has resulted in heavy nutrient loading on a relatively small amount of land. If improperly managed, this heavy load can leach nutrients and contaminants into the environment, which will harm the surrounding ecosystem, waterways, and communities. Additionally, because of rising costs, urban sprawl, and decreasing land availability, it has become more difficult than ever for producers to distribute manure effectively in the Fraser Valley. Finally, stored manure, of course, smells bad and is going to emit greenhouse gas emissions, which can negatively impact farm workers and the surrounding community. So, while manure is a hugely valuable resource for productions, tightening the manure and nutrient management loop in the Fraser Valley can help both the producers and the community. So, we at the SoilRes3 Lab are interested in exploring how biochar can be integrated into manure management systems to more efficiently utilize manure as a resource and benefit producers and the surrounding community. So, what is biochar? Biochar is organic waste burned at high temperatures with limited oxygen to produce a charcoal with multiple different uses. These organic wastes can include forestry residues, agriculture or urban waste, or manure itself. And in biochar circles, we refer to this organic waste as a feedstock. This feedstock is then put through this burning process called pyrolysis to produce the valuable soil amendment of biochar. And there's a lot of research interest in biochar's ability to take an organic waste product and turn it into a resource which can then be fed back into agricultural productions to help with manure management and crop production. So, how do you produce biochar? It's through that process of pyrolysis, which I mentioned earlier, which requires heating organic material at high temperatures with limited oxygen. These temperatures are going to range from 350 to 700 degrees Celsius, with that higher quality biochar being produced on the upper end of that range. Additionally, you need those low oxygen conditions as it prevents the material from burning into ash, as would happen with a regular fire. But you stop it before it reaches that point in producing that biochar. And then finally, baking times can range from 30 minutes to several hours, depending on the scale and method of production and your feedstock. And there's a lot of range in the different methods of production, but the principles of high heat and low oxygen will always be true for biochar. So there are a lot of different methods to produce biochar, scaling from something that can be done in your backyard to huge industrial businesses. And with each comes its own disadvantages and advantages. So this first one is called an organ kiln, and the design is for free online from Kelpie Wilson. And the structure is going to help restrict oxygen when your feedstock is lit from the top. Some advantages of something very small scale like this is that it's going to have a really low upfront cost. It's small enough to be portable, and then it's extremely easy to use. It does not require skilled labor. However, it's going to require a lot of labor, so it's labor intensive, and is going to produce a relatively low amount of biochar. There are more medium scale production methods, which are going to have a much higher capital investment cost, but will also be able to have a significantly higher throughput of feedstock and produce much more biochar with less labor. And then finally, of course, there are these industrial scale biochar production operations, which will have a very high capital investment cost and a very high throughput, and also will likely produce your most consistent high quality biochar. Um, I want to emphasize that these are just three different examples. Biochar production is something that has been investigated really thoroughly, and there are almost endless options for production designs, and these are simply three demonstrative examples. Okay, so the pyrolysis conditions that we just talked about are going to make a difference in the structure and quality of biochar that is produced. So, for example, on the left, we have a very zoomed in image of the microscopic structure of biochar. And that biochar is produced from rice hulls, while on the right, we have a picture of biochar produced from Michigan pine. And so all of this is just to demonstrate that the method of production, your feedstock, the temperatures, the times are going to make a difference in the quality of biochar that's being produced and its characteristics. So it's important to be thoughtful throughout the production process. And it's also important to check for the quality of biochar that you have at the end. Okay, so now that we know what biochar is and how it's made, what about this material is special? So this is that same image of biochar produced from rice hulls. And as we can see, it is highly porous. This structure is fairly similar to that of your common friendly kitchen sponge. And those structural similarities mean that a sponge and a biochar are often going to behave in analogous ways. And there's four characteristics about biochar structure that I'm going to emphasize to better understand biochar's on-farm applications. And the first one is this porosity. The second is the high surface area. The third is it has a negative surface charge. And then the last is finally that it is a very stable material. So I want us to imagine that this is that microscopic picture of the piece of biochar. And so we have all of this porosity, and just like a sponge, when biochar comes into contact with some sort of substance, it is going to be able to suck it up. And so within each of these pores, biochar can hold on to different resources, which is going to allow it to function in a lot of different ways. So the first thing is that these pores can hold and retain water, meaning biochar can improve the water holding capacity of soils throughout dry periods. Additionally, they can hold onto air, improving the aeration of poorly draining soils. They can provide a physical space or microhabitats that fungi and bacteria can thrive in. And then finally, as we will speak more on later, they can be filled with a nutrient-rich source, allowing the biochar to act as a nutrient source in soils. So this porosity, similar to a sponge, is going to allow biochar to suck up whatever material it is in and behave as a multifunctional tool within an agricultural context. The second characteristic I'm going to speak about is that surface area. So again, I want us to think about biochar like a sponge. And if we had a solid sphere, only its outer surface is going to be able to interact with nutrients. But biochar is highly porous, and so that's going to create this massive internal surface area. This means that even a small amount of biochar has far more surface available to capture and hold nutrients as compared to non-porous materials, which is why biochar is so effective at nutrient retention. You're going to get a lot of holding capacity from a relatively small volume. The third characteristic I will speak about is the surface charge. So I want us to imagine we're going to zoom in even more onto one of those individual pores within the biochar. And the chemistry of this surface is going to be a negatively charged. And this negative surface charge means that when biochar comes into contact with a material such as manure or compost. The sponge-like porosity will do that initial work of soaking up that material, but then those nutrients, including nitrogen or calcium or potassium, are going to chemically react with that negative surface of the biochar and create strong connections between the biochar and those nutrients, which will allow them to be retained for longer periods of time. And the final characteristic that I'll speak to is that biochar is highly stable and very slow to decompose. And so this represents an opportunity to sequester carbon in soils, as biochar carbon will not be released back into the atmosphere, potentially for centuries. So now that we know about all of the production, the structure of biochar, how can we use it to help address challenges of manure management within the Fraser Valley? Biochar can help address that first challenge of manure storage, firstly, because excess manure can be directly pyrolyzed to create biochar, and manure can be mixed with biochar to create a valuable soil amendment, both of which will consume manure and create a valuable product. That second challenge of heavy nutrient loads on land can be addressed as adding biochar to fields. Because of that high porosity, the surface area and the surface charge is going to help decrease the nutrient leaching from soils. And that is true for compost and manure piles as well. And then finally, adding biochar to compost or manure piles, in addition to other benefits, will decrease gaseous emissions such as ammonia and help decrease smells. And DeJorn is going to talk more in depth about all of these applications. So just to conclude, the Fraser Valley produces 2.7 million tons of manure annually, and the SoilRes3 Lab is interested in investigating how biochar can be applied on farms to help tighten the nutrient management loop. Biochar is produced by pyrolyzing organic wastes under high heat and low oxygen conditions. And then biochar is going to behave as a multifunctional tool because of its high porosity, high surface area, and negative surface charge. And then finally, biochar is a soil amendment similar to any other in that if it's applied with care, it can help increase efficiency and conditions on farm productions. Or if applied without care, it can certainly cause harm and introduce new issues. And with that, I will pass it back to Essay.
Thank you so much, Karina. That was a really great intro into biochar. We're now going to transition to our next speaker. But just a reminder, if there is anybody who has any questions, feel free to drop those in the Q&A. But we'll continue to take a deeper dive into this. So we're going to bring up to the proverbial stage Dr. DeShawn Bramble. So DeShawn is a postdoctoral researcher and teaching fellow in the Faculty of Land and Food Systems here at the University of British Columbia. His research focused on optimizing essential soil functions to enhance climate resilience and food security. So in this context, he's exploring the ecological benefits of using manure-enriched biochar as a soil amendment, aiming to improve soil properties while promoting nutrient circularity. And so he's going to dive into the application of biochar in the dairy sector. Please take it away, DeShawn.
Thank you very much, Etsy, for that lovely introduction. So at this stage, I just want to introduce to you some opportunities for using biochar in your livestock systems. And keep in mind here that these are only a few examples as to how biochar can be used in livestock systems. There are many others, and I'm sure along the way you'll think of your own unique uses. So one of the first opportunities for using biochar in livestock production is adding it as a livestock bedding additive. And the reason why biochar works, as Karina already pointed out, is a very porous material. So by adding it to your livestock bedding, you're going to help to improve the aeration of those beds. And that means that you're going to have more comfortable conditions for your animals, and potentially that improved aeration is also going to enhance extend the shelf life of your bedding. So that means you're going to switch it out less frequently. Biochar, because it's very absorptive, can lock up a lot of nutrients and therefore reduce the emissions of harmful and very smelly gases, one of them being ammonia emissions. And so when you have less ammonia emissions, you have less of that bad smell that comes from your manure. The studies are showing that by adding about 2 to 10% of biochar in your bedding, you can actually reduce the emissions of ammonia by up to 77%. Now, it's important to note that the main component of ammonia is nitrogen. So also by reducing the emissions of ammonia, you also retain more nitrogen in the system. So overall, you're going to have better housing conditions for your animals while saving nutrients from day one. Okay, so I've got a little bit of, okay. The other opportunity for introducing biochar is in your manure storage. Whether it might be for some of you by adding it to your lagoons or using it as a surface cap if in case you're storing your manure in piles. I should point out here that the benefits are similar to those that I've already introduced, but importantly here, the studies are showing that adding biochar as a manure cap could potentially reduce losses of ammonia by 30 to 80%. And that means that you're going to also cut the odor and emissions and keep more nutrients in your manure. So the main takeaway here is that you have a more valuable fertilizer amendment and you're potentially reducing losses from the system from day one. I know a lot of you might be doing composting on your farms, whether for your own subsistence or for marketing as a commercial product. And biochar can also serve as a pretty good booster of the composting process because, those pores are going to be facilitating the growth and activity of beneficial microbes that are responsible for converting that organic waste into your nice, rich compost. And so what we found from the literature is that if you add biochar at very low rates, even, you could reduce the composting time by up to 20%. So that means that that waste is going to be staying on your farms and in your storage lots for a shorter time if you can accelerate the composting process. Again, because biochar is very good at absorbing nutrients, it's going to reduce ammonia emissions, and the studies have shown that this can be up to 65%. So the main takeaway here is that you have faster composting with more nutrients retained, potentially leading to a higher value compost. Maybe one of the more common ways biochar is integrated into the farm system is as a soil amendment. And biochar acts as a really good soil amendment, particularly because it improves the soil structure, so provides better aeration and water holding. And again, it also increases nutrient retention by reducing losses via gaseous emissions and leaching. But another thing is that by supporting microorganisms in the soil, biochar actually also benefits crop productivity because these microbes are responsible for cycling nutrients and making them available to the soil, to the plants, sorry. I'd just like to point out here that these are some of the many benefits of using biochar as a soil amendment. And if you go to the literature, you'll find that there are a lot of others. So just to reiterate again, biochar can be produced from a range of feedstock, and that biochar, once produced, can be modified before its application to soils. Common feedstocks include manures itself or feedstocks made from crop forest residue. Of course, if you produce biochar from manures, it's going to be more nutrient rich than that produced from the forest and crop residues. And I should point out here that the plant residues, especially those that's woody in nature, are often requiring modifications by a process we call charging, which is where you add nutrients to the biochar because these are, as I said, low in nutrients. So you might ask, if I can directly apply the manure to the field, why is it beneficial to convert it to biochar before doing so? Again, biochar is going to stabilize those nutrients, and the studies are showing that it can actually reduce losses of nitrogen by up to 50% by reducing volatilization of ammonia and nitrate leaching. When it comes to phosphorus, depending on the nature of the biochar, these losses can be reduced by up to 70%. And I know another point that you should consider is that you're going to get a more consistent product. And because biochar can remain in the soil for a very long time, that product is going to likely have more long-term impacts on soil health and quality. So the main takeaway here is that converting your manure into biochar stabilizes nutrients and creates a more consistent amendment with the potential of having longer term soil health benefits. So I mentioned before the whole concept of charging, and charging biochar simply is where we add manure, slurry, or some other nutrient source to the biochar before applying it to the field. And this is usually done with biochar produced from forest waste residues. And the reason why it is done because, as I mentioned before, that those residues in their pristine form are low in nutrients. But remember that we said that biochar serves like a sponge. So you can think about if you apply a sponge in water, it's going to just soak up all of that water, which means that it's going to lock up potentially nutrients that should have been available to the plants. So what we do before we apply the char is to add the nutrients by mixing it with manure slurry. And this is sort of following the idea of feeding the sponge first. So you give excess nutrients so that some can be available to the plants in the short term. Okay, I'm trying to switch the slides, but it's not going through. Okay, good. Right, sorry for the technical difficulties there. Yeah, and so we've been doing some research comparing the effects of charge versus pristine. And when I say pristine, I mean the raw biochar on different greenhouse trials. And I'd just like to share a trial that was conducted by a former master's student, Morgan Hamilton. And here, Morgan planted winter wheat for 2 growing seasons in these columns that you see here. And there were 3 treatments, one being the control soil. So that was the soil just without any organic amendment. The second was the raw or pristine biochar. And the third treatment was where the biochar was mixed with the manure slurry before application. You should note here that the organic amendments were only applied in the first growing season. Coming to a bit of the results from this trial, here I show the yields from the first year of application. And here we can see that the highest yields are observed for the charge treatment. In particularly, you see that there's a 70% increase in yields from the pristine versus the charged biochar, and another 90% increase in yields if we compare the control to the charged biochar. However, in the second year, we only see very slight differences in yields. But if you also consider that year, while there was not much of a difference between yields, there is still some differences that you could see with the uptake of nitrogen in the grains. And this is important because nitrogen in the plant is often correlated with crude protein. So with more protein supplied to your animals, that potentially means that it's going to be high quality milk and meat. Some considerations, however, is that this was a greenhouse trial and field conditions are likely to be more variable and dynamic. And here we also use a very sandy soil with low fertility, but the soils in the Fraser Valley are generally more fine textured and of high fertility. So the yield responses might not be as great as what I presented here. Still, biochar can be of value as the improved nutrient content in the feed can potentially give you a higher quality milk and meat. And of course, the enhanced nutrient use efficiency could potentially reduce your dependence on mineral fertilizer. In fact, the literature is showing that we could potentially reduce your synthetic fertilizer application by up to 40%. So biochar works. I hope I've convinced you of that so far. But the big gap is what works here in the BC context and particularly at the farm scale and at what cost. Certainly, we need more long-term trials to validate our greenhouse experiments. And another big question is also about the application frequency. We've seen that in literature that the application rates are usually over 10 tons per hectare, which is unrealistic. And if we consider BC, we might have enough biomass to apply biochar at 3 to 5 tons per hectare. The other question is, where do we integrate the biochar in the system, as all of your farms probably have their unique setup. And of course, it comes down to the dollars and cents. I've been talking a lot about the science here, but you're going to want to know, am I going to get a buck for my investment here? Unfortunately, there hasn't been really any studies looking at the economic benefits of integrating biochar into dairy systems in the Fraser Valley, but Lee Cartier is going to give you some insights onto how this can be beneficial in the context of the wine industry. So hopefully that would give you some insights. Thank you very much.
Thank you so much, Deshaun. That was a great, I guess, deeper dive into biochar and its potential to support BC dairy as well as other livestock operations. So that's a really good question. I think Deshaun said it correctly. It all comes down to dollars and cents at the end of the day. And so, yeah, I'd like to now introduce our final speaker, Dr. Lee Cartier. Lee is a professor emeritus and researcher at the Hall School of Business and Entrepreneurship at Okanagan College. He's a member of the BC Institute of Agrologists, a retired member, but still still counts, in economics and business management. Lee's research interests are in rural entrepreneurship and the economics of industrial development. The focus of this research that he's going to share with us is on an industry cluster and value chain analysis, business innovation, climate change mitigation adaptation, and the role of the entrepreneur in industry strategy. So as Deshaun alluded to, Lee's going to share his insights into some work that he did on the economic considerations of biochar, specifically for the wine sector. So please take it away, Lee.
Thanks so much, Lovey. What I'd like to quickly walk you through is get you to start to think about agriculture a little bit differently than what we traditionally look at. So I want you to begin to look at agriculture as a circular economy. We'll take a look at what that means in a second. And then I also want to, as Deshaun pointed out and as Lovey has said, look at the BC wine industry as an example of how this might be done and where the benefits might be for them. So let's move forward with it. I think we're moving forward here. Oh, there we go. The research question that I set out to look at is, what is the economic value of transforming the BC wine industry from a linear economy, which is the way it is now, to a circular economy? And the objective of this was to figure out how carbon sequestration technology can reduce the greenhouse gas emissions associated with agricultural practices, and then add value to the industry as a result of that. Just as a definition here, carbon sequestration refers to the process of capturing and storing atmospheric carbon in the soil. So if we take a look at the conventional agriculture as a conventional system, we think of it as a linear economy. And this is a very generic snapshot of it. So you start you start the chain with crop production, and then the crop production from the crop can be then moved on to the dairy or feedlot operator, who uses it as feed source. And then from there, the products are further processed and eventually move on to the marketplace. Now, if we take a look at what the implications are of this type of value chain, we can start with the atmosphere. What is the impact on the atmosphere by these types of activities? Well, first of all, there are greenhouse gas emissions generated from the production of the crops themselves. Secondly, there are additional greenhouse gas emissions produced from the livestock side of the operation. This results in waste from the crop production. It could be crop residues. The waste can take any number of forms. In the wine industry, it's the prunings that come off the grapes. And on the animal side, of course, there's manure waste that's produced as well. Where is the value created in this value chain? Well, there are two sources of value that are created. The first of these is in the crop production, and the second source of value is in the livestock operations themselves. The problem with the linear economy is there is also a loss of value associated with the waste. Economists would consider this to be an inefficient way to produce food. Why? Because of all the value that's lost down here. So what I wanted to find out is just how much money are we throwing away when we pursue this type of system. So let's look at agriculture in a new way. So we go back to the crop production we had here, onto the dairy or the feedlot, and then onto the marketplace. But we're now going to take a look at the emissions. And first of all, you'll find the emissions are reduced, not only from crop production, but from the dairy and livestock production as well. And also, we're not going to throw the waste away anymore. We're going to capture it, and we're going to transform that waste into biochar. The biochar, as Ducharme has pointed out, can then be repurposed and used in the crop production cycle. This now creates a circularity for the industry to work with. And because of that, more carbon is sequestered in the soil. So what was taken out of the atmosphere is now put in the soil. So secondly, we've created new value. So in the linear chain, there was value only created at these sources. We've now created a third source of value for this whole system. And not only that, we've reduced the emissions from it, which leaves society better off. The key takeaway from this, from a business point of view, is that those agricultural sectors that transform themselves into a circular economy have a competitive advantage over those sectors that are rival that continue to maintain the linear agricultural model. So it makes good sense to do this from an economics point of view. I only draw this out because in the case study I'm going to show you, the distances are very large across the Okanagan region. So transporting the feedstocks from the vineyards to the pyrolysis plant is very expensive. So we took a look at whether or not you should use a stationary system like this, or whether we could take the pyrolysis unit to the farm in the form of a mobile one. Just to draw it to your attention, these were two different ways we looked at. The capacities are very different. A stationary has a much larger capacity, but then the smaller scale has a lower capital cost associated with it. So what was the economic value? How much value was captured by the wine industry in terms of converting it to a circular economy? Well, first of all, we found out that we had $3.2 million of industry annual net income. So the farmers benefited from it financially. That turns out to be $2.81 for every dollar invested. So the return on investment is substantial. $1.19 for the vineyards, $1.62 for the wineries. The problem with this is it requires a significant transformation to become a circular economy. The biochar production system has to be integrated into the vineyard business rather than just simply act as a standalone. That means there has to be a change in the way that farmers manage their farms. Secondly, it's an expensive proposition to do this. So as a soil amendment, farmers have to think of this as a long-term investment, not a short-term way to generate cash. So those are some of the things that you need to consider. Here's the actual numbers that come out of these things. So I mentioned that it generates around $3.2 million worth of additional net income, but that's broken down at each of the links in the value chain. So the biochar segment adds another 2.2 million, the vineyards 194,000, and the wineries capture an additional $840,000. So over the life of the study, it's adding around $19 million to the region's economy. We break it down here by per acre or per hectare, so you can see it's just the same numbers divided by the number of hectares. The thing that I want to draw your attention to is up here. This study treated the BC wine industry as a closed economy. What that means is that there were no inputs transported into the sector. So all of the biochar was produced strictly from the waste generated by the vineyards and the wineries. No additional feedstocks were used. So if you took all the waste, converted it into biochar, you could treat 288 hectares or 710 acres with biochar. That gave you an additional income of $3 million a year. Remember, there's 10,000 acres of vineyard in the Okanagan. So if you were to import feedstocks from other sectors like forestry, you could multiply that number 10 times. So you wouldn't have 3 million, it'd be 32 million, and not 190 million of economic value. This whole thing excludes the potential sale of the soil captured carbon into the carbon offset markets, which would add another source of revenue for the farmers. The sensitivity analysis looks at where's the risk associated with this whole value chain. We're selling, biochar has a market value price of around $1,000 a ton. So of the value variables we looked at, the selling price of the biochar, the variable cost to produce it, the capital cost of the equipment, and the biochar production yield itself, the single biggest variable that had the biggest impact on risk was the selling price of the biochar per ton. So just to draw that to your attention. So here are the numbers for the Okanagan's wine industry. There are 7,000 tons of grape prunings burned every year. Pumice generated from the wineries is another 3,500 tons. If we transform that waste into biochar, we're able to capture another 9,000 tons of carbon per year. If we were to sell that carbon for $47.64 a ton, it would add another $178,000 worth of revenue to the industry. This is why it creates a competitive advantage over wine regions that simply have chosen to stay with the linear model. So these are the conclusions. First of all, there's increased profitability of transforming your sector into a circular economy. And for the wine industry, it helps them achieve their sustainability goals. There are risks associated with it very clearly, and those risks of adoption are due to the production costs, the application rates, and potential yields, but there's also risk associated with the price of biochar itself. The other piece I'd like to leave you with is that biochar produced from agricultural waste is an effective way to sequester atmospheric carbon. And the scalability of the technology really is an important factor here. If you're dealing with a lot of small acreage farms, trying to transport all of that waste material to a central location can be very costly. An alternative is to simply put the pyrolysis machinery onto a trailer and to simply take it to the individual farms. So that's essentially my story. And at this point, I simply look at the potential future. So I believe it's back to you, Lovey.
Yeah, thank you so much for that. I guess, introduction or guide through the research that you've done for, in the wine sector. Obviously, we try not to compare apples and oranges too much, but that's really good context to give at least a high-level introduction as to some of the economic implications. So that brings us to the end of our presentations. I'm going to bring Corinna back to the stage just to share the conclusions, and then we'll jump into our Q&A. Please go ahead, Corinna.
Thank you, guys. Yeah, just to give a quick overview wrap up. First, biochar is going to provide an opportunity to turn organic waste into a valuable soil, manure, or compost amendment, which can help farms address challenges associated with manure management as well as other farm production challenges. It can be used across productions, including in bedding, composting, and manure management, and field fertilization, as Deshorn spoke about. And then because of Fraser Valley's fertile soils, biochar likely will not have a large impact on yield, but could add value from that decrease in necessary mineral fertilizer input. So, oh, oopsies. Finally, as Lee just spoke about, capturing waste from the value chain can generate additional profits for agricultural productions. And this was true in the BC wine industry case study that Lee described. But this analysis, to be clear, has not been done with the BC dairy industry. Yeah.
Wonderful. Thank you so much, Corinna, and thank you to our three speakers as well. We've got some great questions in the Q&A, so I'm going to stop sharing my screen and we're going to bring our speakers to the stage. If you could do that for me, please. Tech support, thank you. And yeah, so we've got a couple of great questions here. I'm going to start with the one in the chat box from Elizabeth, who's asking, does it make economical sense to produce and sell biochar, or is it best to use it on farm? Lee, maybe you could address that one for us.
I was really hoping somebody would ask that question. The reality of it is that biochar is very valuable. So if you produce it from the waste, you can sell it into the marketplace. And the bulk price of biochar is around $1,000 a ton. It varies from 800 to 12 or so. But if you were to put it in bags and sell it into the garden center market, it's about $4,000 a ton. So there's a real incentive for the production side, the biochar production side, to just simply forget the farm and sell it in the market. However, that looks at it through only one link. Remember, it's a value chain. So the biochar is only one link, and yes, it does create value. But if you remove it from the value chain and simply sell it outside, you lose the value all the way down the value chain. So if you add it all together, often you get more out of the value chain than you do out of selling it in the marketplace. So I hope that answers your question.
Thank you, Lee. Does anyone else want to add their thoughts on that question, whether it makes economical sense to sell and produce, or produce and sell rather, or just to use it on the farm? Or if that's very good. Sweet, no worries, cool. Okay, we have a question here from Tyler for Deshorn, Dr. Bramble. How did you control the quality, the porosity, the pH, etc. of the biochar used in your study?
Oh, good question. So the biochar used in this study, we actually purchased it from a commercial supplier. With regard to controlling all of those properties, I think once applied to the soil, those things are going to be changing. And as I mentioned before, and Karina pointed out that the char that's produced would depend on the pyrolysis temperature and the feedstock. So it's not that we control these parameters. They just kind of depend on how you make the biochar.
Thank you. Go ahead.
Maybe, yeah, may I add something? Yeah, because yeah, that's a very good question, Tyler. Because first, when we use the biochar that Dishon was describing from BC Biocarbon, we are like a bit shooting in the dark because we don't know the characteristics of the biochar initially. But then what we used to do and what the farmers or the researcher have to do, in fact, is to send the sample to a certified lab to get a biochar certificate to be sure that the quality, so the pH, as you are mentioning, the nutrient content, but also the heavy metals content is not too high to avoid some contamination of the soil. And there is one in the US and one in Europe, I mean, lab to get the biochar certificate. So that's another point that we have to keep in mind. Yeah.
And Tyler had a follow-up question. They were just wondering what the feedstock was, if you knew of that biochar that you used in the experiment.
I think it was a forest waste residue.
Mhm.
Okay.
Thank you. We have another question here from Christina, who's asking, given that dairy is a liquid manure, will farms have to also invest in the solid liquid separation as well as an initial step in the biochar process? Oh, as an initial step in the biochar process.
I can start for this one. I think that's an amazing question. And I think one of the things that we were trying to emphasize is that application of biochar and the production of it is going to look different depending on what your production looks like. And so if you do not already have like a solid liquid separation, it might not make sense, but you could still use your manure to charge your biochar and then apply it to your field, or, I mean, kind of like Lee was saying, you can sell it as a very high value fertilizer to other people. So maybe you have some sort of other source of organic waste. I know we're working with a farm out in Abbotsford who gets a lot of oat husks from a local bakery that they then use in their compost. And so finding a different source of organic waste, combining it with your liquid manure, and then using that as opposed to investing in that initial separator as well could be good. So yeah, it's very adaptable, I think, to whatever your farm system is going to look like.
And just to paraphrase, I guess what we're thinking here is that there's you could either purchase biochar and then charge it, or you could make that biochar from any carbon heavy feedstocks that you might have on your farm and then charge it. So there's lots of different opportunities there, which is really great. We have a question in the chat from Stuart, who's asking, is it known if biochar is useful as a means of reducing contamination in soils, for example, heavy metals or microplastics? It's an interesting question. Thank you, Stuart.
Thanks. Very good interesting question, Stuart. And yes, it is used as a remediant in soils. So again, depending on the feedstock and the method of pyrolysis, it can serve to remediate soils by locking up cadmium and other heavy metals. And there's a lot of literature on that. So
I can also add in. So, like Deshorn said, there is quite a bit of research on it remediating, especially heavy metal contamination. I don't know about microplastics, but the principle behind it, I think, is applicable to this webinar as well, where if you put an uncharged piece of biochar, that porosity and surface area is going to suck the heavy metals onto the surface, which is the other reason why we are very strongly cautioning against applying a woody-based biochar uncharged to soils, because then if you're taking that uncharged piece, putting it into a soil, it can also suck up the nutrients that you have applied to your field and hold them onto the biochar rather than releasing them to the plants. Yeah. Thanks, Stuart.
And there's a few questions from Tyler here. I'll just get to the ones in the Q&A first. Tyler asks, are the transportation costs considering fossil fuel versus electric transport? I think that's for Lee's study in the wine sector.
Okay, I think if I understand the question, it's the cost, the transportation cost itself, but you also want to look at the environmental impact of that as well. That's a really good question to which I really don't have a clear answer for you. The transportation cost that we looked at for the case study that I showed you was $20 a ton. That's what it costs to truck the feedstock from the farm to the pyrolysis plant. The greenhouse gas emissions are going to be significant by doing that, especially if you're using diesel-fired trucks to transport it. The greenhouse gas emissions should be less if you're using a mobile unit because you're not making as many trips to deal with the production. So you're taking the plant to the farm rather than taking 20 loads to the pyrolysis unit. So I would expect the greenhouse gas emissions would be fewer based on the mobile unit. I hope I've answered your question correctly.
And how do you monitor the contaminant level of manure-based biochar to make it applicable for SoilRes3? I'm not quite sure what that means, but hopefully you understand that one, Lee. CO2 removal credits. Thank you, Tyler.
Are you interested in the carbon markets here? Is that what you're looking at?
It looks like, yes, looking at the carbon markets.
This is an area that I really have become very excited about, to be personally honest with you. And it's an area of research where I'm just starting now. We've just got some funding for it. There is potentially huge benefit to the farmer becoming a carbon farmer as well as a food producer. And the reason for that is that you can sell these carbon credits into the voluntary markets quite readily. The issue that we're running into here is that what's it cost to do that? To establish the protocols required to access the markets can be very expensive. We have not worked that out. We don't know what it's going to cost to participate in these markets. I'll know a lot more about that by the time we get to the end of the study. But I'm hopeful that it is. One of the factors that's important in establishing the price of these carbon offsets is how long the carbon is stored in the soil. So what they refer to as low value offsets are those things like planting trees. Well, sure, you have a carbon offset there, but it only lasts as long as the tree. And then when the tree is gone, it's back in the atmosphere. Residual crop residues that are chopped up and put into the soil have the same problem. They don't stay in the soil very long. So the market's not prepared to pay very much for those. Biochar is unique because it'll stay in the soil for hundreds of years. So it's considered to be a high value offset. Markets pay more for that. How much more? I don't know.
May I add something? Yeah, thanks, Lee. It's very insightful. And from a very soil science point of view, in terms of the carbon sequestration and CO2 removal credits, we have to keep in mind also that it's not only a question of putting a lot of or storing a lot of carbon in the soil, because we can put a lot of bad carbon in the soil, like very recalcitrant, not easily to be used by microbes, which is not good. The very point is that it's to find a good compromise in terms of the quantity of biochar and also charging the biochar for activating the processes in the rhizosphere and the microbes associated with the roots. So that's not a question of quantity, but also the quality of the organic matter we're going to put in the soil.
Very good point. Excellent. Okay, we have I think we have two questions from Andrew Reisman. Is the syngas ever used? I think that's in referral to the biochar production. And the second follow-up question is, what's the energy cost for producing biochar versus buying nutrients? Looks like you might have an answer for that, JT.
No, just to say, Andrew, thanks for the questions, because the second one, yeah, is particularly a very good one in terms of the energy cost. The only thing I can say from the work that we were doing also in Burkina Faso in Africa is that we can reduce the application rate of mineral fertilizer by charging biochar with manure, but also with liquid fertilizer. So that's a way to reduce the cost of the use of mineral fertilizer. But compared to the production, I don't know. That's a good question.
I think I can add on really fast. So I talked a little bit about the different methods of biochar production, and kind of like I said, I mean, the possibilities really are endless. People have thought about it a lot. And I have seen some very cool designs of biochar productions that you are obtaining like bio oil and syngas out, and then also having a process where the heat from the initial investment of making the biochar, that heat is then used to like dry the feedstock and continue. So it's kind of more or less self-sustaining in terms of that method. So I don't know the answer to the other question, but I do think that there's a lot of space for very creative people, engineers to come in and make it into a very sustainable process. So.
Yeah, the circular economy is an emerging field in the BC agricultural sector, and so there's a lot of space for innovation in that field. Okay, we have about 5-ish minutes left, so we have about 3 more questions in the chat. We have Tyler asking, with 3 to 5 tons per acre application, how frequently do you see making that application, and how many acres would we be looking to address for in the Fraser Valley and other regions? I think that's probably to Deshawn.
Yeah, maybe I can start with at least the first part of the question. Very interesting question, Tyler. So I think that's a big question as to how frequently do we need to apply the char to actually maintain those responses. But that depends on the biomass that we also have available to produce the biochar. And so some work that was being done in the SoilRes3 Lab shows that if we take, for example, forest waste residues, there is enough biochar in BC to apply maybe that 3 to 5 tons every 5 years. So you could choose to do it that way, or you could apply 1 ton per year for 5 years. The second part of your question, how much acreage we are looking to address, I think that's probably more of a question for the actual people who would potentially be using this amendment, so the farmers, and of course, if this initiative is supported by governments and agencies, then yeah, the possibility is endless, but unfortunately, I cannot comment on that at this time.
Okay, 2 final connected questions. This is from BJ Mills. Would low nutrient, so I think we sort of answered this, but so would low nutrient biochar made from forestry waste remove nutrients from the soil if not charged first? I think we can answer that as the answer is yes. If that is the case, when or how could those nutrients be released back and made plant available? So I think this question is around the pristine biochar. Is there a time period in which those trapped nutrients will be released over?
Yeah, I think this time scale can vary from months to years. Typically, as other amendments of even compost, you tend to apply these organic amendments maybe 3 months before you actually plant so that you can actually have some degradation of the amendment, and the microbes that are locking up those nutrients after you apply them, they can then be releasing back those nutrients back to the soil before you plant. So if you're not charging your biochar with nutrients, yeah, you better apply it some months in advance of planting.
And I guess a very related question, would annual tillage reduce biochar's residence time or stability in the soil?
I can maybe take this question.
Please, JT, go ahead.
Interesting question, Stuart. Just because we did a very long-term experiment in Belgium a few years ago, and we have seen that biochar can be really stuck in the aggregates of the soil, and we know that the TDH can break down the aggregates, so we can assume that the stability and residence time of biochar can be reduced through the TDH process.
Maybe to add on that, JT, and again, JT identified that there are different fractions of organic carbon in the biochar. So the more quote unquote recalcitrant or chemically stable fractions might be less susceptible to that effect.
Excellent. Wonderful. Well, we are getting to the end of our session today. So make sure we don't go over time. Just going to transition us towards the end of this presentation, if I can find my screen again. So yeah, thank you all so much for joining us. And this has been a really engaging discussion. There's been some really great questions popping up from the audience. And so if you have any final questions, feel free to drop them in the chat and we'll make sure to answer them and share all the answers to these questions at the same time as we share the video. But you may be wondering kind of what comes next for this project. And so this is the beginning of a long pathway for the SoilRes3 Lab, of the beginning of a project. So there's a few ways to kind of get involved with ongoing trials. So there's going to be, the team is working on soil nutrient and odor trials, as we've mentioned today. Also testing application rates and frequencies. And to kind of support building out kind of on-farm evidence, the team has also created this producer survey that any producers on the call today can take and share some of their thoughts around the use of biochar in their operations. And there's also going to be additional demonstration days throughout the summer of the growing season of this year to bring people together to actually see some of the work that's happening on farm as well. And so we've dropped some of the links in the chat for you so you can check out those specific pages. And then also you can also feel free to scan this QR code. It'll take you to a Linktree page where you'll see all the links as well. But again, all of these links will be in the follow-up email, so you can feel free to take a look at that email when it comes out in about a week. But if you have any questions or would like to continue the conversation, it's been a very rich discussion today. You can feel free to reach out to the research team at lfs.soilres3@ubc.ca. And as always, we really appreciate any feedback that you are able to provide about this webinar. So you can feel free to scan the evaluation QR code. The link to the webinar feedback is also in the chat as well, so you can check that out too. We're 2 minutes before the end of our session. That's amazing, I think, for a lunch and learn. But thank you again, everyone, for joining us today. If you have any feedback, please feel free to reach out to our team. And yeah, enjoy the rest of this bright and sunny day.